everyone, today's approach is about a motor, an electric motor to be precise. Before getting into details of what the motor is and the theory behind it, I would like to tell you that you will always have a timestamp below in which you can follow and go to the place you want to watch in this video. Since I'm doing this for university, I do need to talk a little bit of the theory behind the motor itself. If you want to go already to the simulation, just follow the timestamp. So today I'm going to talk about the motor and do the simulation using the Ansoft Maxwell software. So the flux of this video goes all the way through the theory, then goes to some software overview since we're using another kind of solution type today, and then go into the geometry, solution, and results. So let's move forward to the theory now. So here we are in the theory background. In order to understand how an electric motor works, we need to understand what an induction is. So according to Maxwell's laws, one of which the Faraday's law, anytime you have the variation of flux, you're going to have the creation of a current and also an EMF. The idea is that a motor itself is creating some movement, and the movement shifts the flux. Because of that, you have the displacement of the flux throughout time, and that's going to create a current. Actually, some motors do in this workflow and others do in the other workflow, in which is by a current, and this current do the job of creating the motion in the magnet. But today I'm using the idea of by sweeping a magnet, and by doing so I will be creating a current. And that's what I brought here in this image from the Sears and Zemansky book. And the idea here is that you have the displacement of a magnet going through a solenoid. And if the magnet is stationary, you have no variation of the flux. By not having so, you have no EMF and no current at all, no induction at all. And here, by moving the magnet, you do have in the galvanometer the induced current. And you could also do the same thing with an electromagnetic solenoid if it is charged into some battery. And that's going to show you the same thing. And by doing so, it also shows that you don't have to have a permanent magnet involved in order to create a current by the variation of the flux. You could always have another electric magnet as well. And also, any kind of change into the flux is going to create the EMF. So you can change the geometry, you can change the current through time, you can change the movement, you can move around the object you want around the other object that you're interacting. So these different kind of ranges gives you different fluxes, and by doing so you have a variation of flux and then an EMF being induced and also a current being induced. And here in the experiment I did is just by doing so. You have here this cylinder-shaped region, which is the outside layer of the cylinder, and then you have this inside layer cylinder with this rectangular shaped in which is a magnet doing this circular movement around the z-axis. And by doing so, it is inducing a current in the simplified coils that you see here with this cylindrical but with a less radius shape here. And the arrows here, they are due to the ampere per meter square induced current. And this is what we are going to simulate today. So let's move forward to a software overview in order to understand a little bit further of what we are going to do. Well, so here we are in the 2D interface of the Ansoft Maxwell software. I already chose the solution type to be transient. Now I need to do an overview of what the transient solution type is, in order for you to understand what we're going to do here. Essentially, the transient solution type computes magnetic fields in the time domain. So that's important. And the way it computes is by instantaneously at each time step. During the video, you're going to understand what a time step is. And the source of the static magnetic field can be an arbitrary time-varying current in conductors or a permanent magnet. And that's the scope we're aiming here. And that's the main idea. So the project idea is to construct this electric motor and to calculate the magnetic field and the current density, both in the zone of interest and in the coils, simplified coils I create here. So let's move forward a little bit further into the geometry itself, and as I move on, I'll be explaining the runabouts into the solution type. So let's move forward to the design and geometry of our project here. Okay, so we are in the 2D design. I already changed the transient mode, in which is the 2D, as you can see the axis here. So the idea here is to create that model I showed in the Fourier background, in which you can see right here. And to create that, I want to do a 2D design of it and then extrude to the 3D design. First thing I would like to do is to draw a rectangle here in this plane. I'll set some values here, but first I would like to start it as in the beginning of both axes, x and y. And by the ranges here, I want to give it in the x-axis 2 millimeters and in the y-axis 8 millimeters, and that will be okay. I will need to zoom out a little bit in order to see the whole rectangle now. I was too zoomed in before. Okay, first thing I would like to do is to duplicate both here, unite them all using the Boolean operator, and then do the same thing with the x-axis, and then unite them as well. I'm choosing the Boolean operators to do it because it's faster and easier to do that and put the center of the coordinate system to be right in the center of it. I could have started the rectangle by choosing the coordinates to be in this way, but it's a bit more complicated than the way I just did. So that's why I did that. So I'm also doing something here, which is creating a small cut around the rectangle here in order to represent a magnet. Okay, so the first thing I'll do is press the magnet and then the circle and then do the subtract Boolean operator. And by doing so, I do this smooth top here in which this is to be the magnet. So since I already named it the magnet, I'm naming it here as well. So this is going to be the magnet. Very good. I'm already changing the material as well, and this is going to be a neodyme alloy. It can be the neodyme 35 or the 31, but for each one of them, if you choose, you should clone the material. And the reason so is that you want to edit some of its aspects, and you don't want to change the library standard one. You want to change your own. So I'm doing here, changing its name, putting clone, and also changing the component in the y-axis to be 1. And the reason behind that is, as you can see here in the geometry, so what I want here is that I want the magnetic field to be going out in the input of 1y. And the idea by doing that is that I am directing the magnetic field. I am putting some directions into the magnetic field. The same thing I did in the Hallback array videos I have here. Okay, so the next thing we should do after creating the magnetic geometry is doing this thing called a band. And in the transient mode, a band is going to be this region in which everything inside of it is going to move along with the same radius. So you won't have relative motion between the things that are inside the band. The band is moving as one. So when conceptualizing the cylindrical rotational motion, the band and the objects that are inside it will be moving and rotating by one, and by doing so they will not be remeshing between. And the meshing idea I'm going to explain a little bit further. Okay, so let's draw this band, and it should incorporate the magnet itself. Since it has 8 millimeters in the y-axis, I want to create it as at least with a radius of 8. So I'm putting a radius of, let's say, 9. Okay, this is good. I'll put also what we are going to name here as the coils. And the coils I wanted to start, let's say, at the 10 millimeters in the y-axis, and to have a 1 millimeter, 0.5 millimeter radius. And that's what we have here. So by doing so, I could also do some motion, which is called duplicate around axis, and that's what I want to do. The idea here is that in my project, I need to have 4 of those, which I'm calling here coils. And by duplicating around axis, I can choose the z-axis, which is coming out of the screen here, and put the number 4 in the total number duplication here as a factor of 90 degrees from one another. And that's going to create the 4 small circles here, in which I'm calling them the coils. Very good. So now that I have the coils here, the next thing we should do is create a region that will be incorporating the whole system. And this region should be one that is going to be at least bigger than the whole system, logically. So I'm choosing the center of the geometry as well. And also here, since I know the size of the small circle here and this one as well, I'm choosing this to be as a radius of 15. So by doing so, I create this region around the other geometry I already have. So the first thing we should do here, after creating this geometry we want in the 2D design, is to name what we have. So this, as I mentioned before, this is called the band. The band is this area in which everything is going to move as one when we put some motion here. So I named the band first, then this is the region. So I'm calling it region. And it takes a little bit to write it down, but it saves a lot of time later. Okay, so the circle 3, 2, 3, 1, and 3, 3, and the circle 3 itself, those are the coils. Very nice. And now that I have all named up, I'm going to assign a material to the coils as well. I want the coils to be a conductor. So in order to do that, I'm assigning them the copper, in which is a conductor, of course. And so also to ease up a little bit, I'm also putting some transparency in the region in order to see a little bit better, and also in the band a little bit, just to see it better. Okay, so now that we have the geometry created, we need to assign the band to the geometry we want to be the band, and also we want to put some excitation in the coils we created. So in order to do that, let's start with the band, in which I click here with the right click of the mouse and assign band. By doing so, we have this motion set up. Remember, we are in the transient mode, so we want this to be rotating, and we choose the rotation type, and the rotation axis should be the z-axis that's coming out of the image here. And the mechanical part of it is also important because it's showing us how the system is going to move around the z-axis. So the first thing I want to do here is to choose the system in which it's better for me. Now I'm choosing degree per second because that's what I want, and now I'm also choosing 360 degrees per second. So it's going to give a full turn in 1 second. Very good. And that's all we need for now for the band. And now for the coils itself, I want to assign them excitation. But in order to do that, I'm just going to hide the view of the region here just for a little bit, and then pressing each one of them with the control button. Okay, so we go here to excitation and we go to end connection. The idea behind end connection is that this causes all objects in the group I just chose, which are the coils, to be connected electrically in parallel using a finite resistance and inductance. And the idea here is that those are used primarily to be in passive conductors, such as in this rotor here, since what's going to be creating the magnetic inductance in the coils is the magnet itself. And that's what we want. We don't want to assign any current here. I just want the Maxwell to know that those conductors, they can have current. And this is what I'm going to do here by choosing a resistance between them and also giving it a small number since we're talking about small geometries. And I'm leaving the name as N connection 1. So this is going to tell that this is a group of connected in parallel coils. This in the 2D in the 2D design, this is good because we want to create a graph between the induced current and time, and that's a way of creating that graph. And later on, I'm going to extrude this to 3D. Very nice. So now that we have the currents here and everything that we want, I also need to put some eddy. And that's what we're going to do now. We go to assign excitation as well, and we go to set the eddy effects. And we want to choose the coils. Nice. By doing so, we move forward to the setup. Okay, and it's nice to understand here what's going on. And the first thing I would like to notice is that here, in contrast with the magnetic static solution type from the previous videos, we do not have any information about convergence itself. And that the reason why is because in the transient mode, we have no adaptive passes. So there's no adaptive solution to converge with. So for each time stop here, so for each time step, we have a mesh being created between the meshes in the band and the meshes on the outside of the band. So this is what we have here. So it's really important since we do not have an adaptive solution type. It's really important to do a good meshing, and that's a parameter we are going to put later on. So I want this to perform in 1 second, so it's going to stop after 1 second. It's a good practice to put 20 time steps through rotation. So I know it's rotating in 1 second, so I want this to be 1 divided by 20, which is 0.05. Okay, and another thing to do is to save the fields by putting the same parameters here. And by doing so and adding to list, you're saying to the solution type that you are going to save in your memory, in the computer memory, the results for each one of these time steps here. And that's really important if you want to see better results in the future and save the results as well. Okay, so now that we have the solution setup done as well, let's check how our validation system is. Just before doing that, let's show the region again. So we have the region here. So with the region here, it's also important to name the boundary. And by doing so, we select edges and then we go to assign boundary and put the balloon boundary. This is going to create a boundary in the outside layer of this geometry we named, and everything inside of it will be a boundary. After that, we want to choose all of our geometry here and put some, oh my bad, we choose objects now, it was choosing the edges. So we choose all the geometry here and we are going to assign a mesh operation. And it's going to be length based, and this is going to be of 0.1. So we want to really refine our mesh. The idea here is that since we do not have an adaptive pass, we need to have a good mesh. So by refining the length of the elements inside of our mesh, it's a bit more interesting for our results to converge in a better related to reality sense. And also, I would like to choose the geometry again. Actually, I would like to choose the band and assign a mesh operation here as well. And it's going to be a surface approximation. By doing so, I'm also applying this into the surface. And the aspect ratio will be 5. Okay, nice. So now that we have the mesh being refined and also the region of our geometry being defined, we move to validating. Everything seems okay, and we go to the solution now. It's going to take a little bit, so I come after the analysis. Okay, so now the results are complete, I would like to show you some results. First one will be the graph between the induced current through time. So we are in the y-axis here, so we are going to choose here. It can be position, my bad, it can be any connection, which is the current, and then we're choosing time. Let's see what we have. Okay, so now that we have here the current and time graph, we can do some we can have some understanding of what's going on. So we have the current being in at minimum value here right at the beginning and right at the end. So the first orientation of it is giving a negative current, which is just a matter of direction. And also when the magnet is on the other side, 180 degrees to the other side, which is around here in the half of the distance, and thus half of the time as well, since we're talking about a constant movement through the circle, a rotational and constant movement, we have the peak to be here as well. And the idea here is that we have the derivative of the flux to be 0 around 35 seconds and around 75 seconds as well. And this is happening in the position in which is around the angle of 19 degrees, in which you have the magnetic fluxes to be 0 due to the cosine of the angle of the unitary angle of those coils between those coils and the magnet to be 0. Okay, so let's move forward to the model and go to the 3D design now. So we have done everything we needed in the 2D design, in which was to inspect the current and time graph. So by clicking with your right button in the Maxwell 2D design and go to create 3D design, we can extrude along the z-axis. And I want to do this as, let's say, 5 millimeters. And all of our geometry will be extruded in the z-axis. So we have the same geometry here, but now on the z-axis. Okay, so now we are in the 3D design. And remember that we have to change the solution type to transient. So let's do that. Okay, so let's check what we have to do. By validating, we see all the mistakes we have, which are not selecting the eddy effects and not putting analysis setup. So let's do that. So the first thing we should notice here is that it doesn't have a band as well. So since once we extrude it, it doesn't have a band. So I'm also applying a band here. I already have the names for the band and for everything from the 2D design. So let's assign a band in here. By assigning a band, we're rotating around the same z-axis and giving the same rate of rotation through seconds. Okay, so we have here, we have the band assigned, and now we have these simplified coils. They're not even close to be real coils, but it's good for the relation we're going to do here. But they're only here to simplify things. They should not be taken as real coils. And as a first approach, it's reasonable to have coils like this as simple as possible. And also in the 3D design, you should be asking yourself, why not put some eddy excitations as you chose before? Well, the reason why is because here we don't want to have those here because we are not assigning a direct current to it. So I only saying to the software here that I know that I am not setting an eddy. By clicking here but not choosing anyone, it already knows that I don't want to choose none of them. Okay, and now you want to put some mesh operations in it. So you select the geometry, all of the geometry, and you put some mesh operations here in order to refine your mesh. The idea here is that you want to just put like this maximum lambda to be a little bit smaller than this. Let's say 1.5. Okay, and this is good. And also, I want to put some amount of cells in the band. Hold on, just a second. Yeah, so this will be like 1,000 cells in the band already as it is, but in the region I want it to be bigger. And the reason why is that I want the region and to scope all of our calculation here without lacking cells. So I am increasing the maximum number of elements here and also decreasing the maximum length of elements to 3. Okay, so this should be okay. Let's check if everything is validated, and as it is, let's move forward to the simulation itself, and I will come back after it's done. Okay, the simulation is complete. So first of all, we want to change the time step here to be as 1. Since as default, it goes to -1, in which it doesn't exist in our system. Let's move to 0, and I mentioned 1 before, sorry. So let's move to 0, and this is the first time step we have. And let's choose one of our planes in order to see the magnetic field and the current density in the coils. So the first thing I want to see is the magnetic field in our solution. So let's choose vectors, all objects, and see what we have. Okay, so as a first display, I'm not seeing much. I would like to, first of all, change a little bit of the transparency of our band. And let's say like this. And also, I would like to, okay, it's saving some things. And also, I would like to change some of our configuration here in the representation of these vectors. First thing I like to do is to to put the sizes a little bit down here and map size. So this will give us all of the vectors inside of the area here. And okay, I'm also putting some transparency in our magnet as well, so we can see what is happening inside of it. Okay. Okay, so now that we have the magnetic field displayed, I also like to display the current density. And to do that, I would like to select the coils and then apply the field I would like to see, which is this field here. Okay, so after done that, I have it here, and I'll do some animation in order to see what's done. But since I have the animation here done already, and the only difference here is the diameter of the coil, I will show this one since the animation takes a little bit to be completed. And this is what we have. So we have the magnetic field rotating around it, and it is creating this variation of the density that goes up and down, and there is a point of minimum and maximum and a point of 0 according to where the flux go through the coil. And a better and more specific inspection would show a more detailed analysis over where and at which angles you have the best improvement of the density, the best amount of the best amount of current density here, or the lowest amount here. But since this is not the scope of the simulation and only to show how you can achieve that, I'm going to stop here. So for that, thank you very much, and I see you next time.